We have a classic physics problem to work through here. There is a box that is on an inclined plane, and we're able to change the angle of that inclined plane, make it steeper and steeper and steeper. And the question we want to address is, given the coefficient of static friction, when is this box going to start to slide down? Okay, and we are given a value that the coefficient is static friction, so mu sub s is 0.4. We are not given the mass of the box, and in fact that does not matter. I'm going to pick, for applying Newton's first law of motion, coordinates where x is parallel to the inclined plane and going down, and y is perpendicular to the inclined plane and going up. The first thing that we want to do is fill in the free body diagram for the box. So the box obviously has weight, and that weight is going to act at the center of mass of the box. So I'm going to put a vector straight down for the weight. All right, now what we want to do is put in a perpendicular, so drop a perpendicular to make this weight be the hypotenuse of a right triangle. And for that right triangle, the adjacent side is perpendicular to the inclined plane, and the opposite side is parallel to the inclined plane. And what you can convince yourself of, if you think about it carefully, is that if this angle is theta, then this angle has to also be theta. Okay. Because theta plus this angle is going to be 90 degrees, and so though going around on the other side, this has to also be theta. All right, so the weight of the box has a part that is directed perpendicular to the inclined plane, so there's its y component, and it has a part that is parallel to the inclined plane, so there's the x component of the weight. So F, G, the y component, and F, G, the x component. All right, for that box to begin or remain at rest, so far it's in free fall, so that's not going to be what we want. There is going to be a normal force exerted by the inclined plane that is just a big enough vector to cancel out the y component of the weight. So there is the normal force, and if this is just right before the box starts to slide, we're at the critical value for the force of static friction, and then the force of static friction is going to be just big enough to cancel out this component of the weight, the part of the weight that's parallel to the inclined plane. So there is going to be a force of static friction going up, and since this is right before it starts to slide, I'll go ahead and put in the max. And then looking at our vectors and applying Newton's first law of motion, this force cancels out that component, and the normal force is going to cancel out that component, and we have the net force equal to 0. All right, so let's apply Newton's first law of motion and go through in detail and see why we actually do not need the mass of the box. So the sum of all of the y components of forces is equal to 0. So Newton's first law of motion, that tells me that the normal force, which is pointed up, and this component of the weight, which is pointed down, which is minus Fg cosine of theta, is going to equal 0. And that tells me how big the normal force is. The normal force is the weight of the box times cosine of theta. Adding up the x components of forces, sum to 0 in Newton's first law of motion. So now I've got this part of the weight in the positive direction. So it's an Fg sine of theta because it's on the opposite side of the triangle. And then going up the inclined plane is the force of static friction, and if it's right before it starts to slide, that is the one we have an equation for. It takes the maximum value. Those two forces right before it starts to slide add up to 0. So what can we say? I move force of static friction max to the right hand side. We have Fg, the weight, times sine of theta is equal to force of static friction, the maximum value it can take. And we know what that is, because we have an equation for it. That is coefficient of static friction times the normal force. And we know that the normal force is as big as the weight of the box times cosine theta. So we can pop that in. Cosine of theta. All right, so let's put everything on the same line here, and we can simplify a bit. Fg, the weight, times sine of theta is coefficient of static friction, Fg, the weight, times cosine of theta. It's the same weight on both sides because the weight is causing both of these contact forces, the normal force and the force of static friction. So that cancels out. And we recall that tangent of theta is sine of theta over cosine theta. So divide both sides by cosine theta. We have that tangent of theta is equal to the dimensionless coefficient of static friction. And then I can take an arctangent of both sides and find that the block or the box will start to slide at the arctangent of the coefficient of static friction. We were given that that was 0.4. So 0.4. And when I do that, I get basically 22 degrees when the box starts to slide.